Okay, so now we're recording the lecture. So let's go through the assignment. Okay, so the goal of this assignment is really just to get you guys some more practice with web scraping and collecting data from the internet, right? And I figured, best place to go or best place to collect data from if we're worried about legalities, let's just take our own school's data. So for problem one, I gave you guys basically links to basically the three main departments at CGU, right? We have the econ department, we have the psych department, we have information systems. So if you go to any of these links, like let's say our glorious economic sciences department, right? This is the home page you get. You get some description about the department, and then here you start getting a list of all of the faculty members, right? All of which have a photo, except for me. Okay. So what I asked you guys to do in this first on this first problem was to keep it very, very simple and to use the rvest package to just extract everything on this website or on this web page that has that's embedded inside of a paragraph tag or a p tag. So the trick we covered last week in class was if you right click on any page and you click on inspect, when you click on inspect, you'll be able to see all of the actual HTML code. And actually in this HTML code, you can even do things like Command F or Control F, and you can look for like a P tag. Okay, so here's all of the P tags on the website. All right, so there's a header, welcome to the economic sciences department, and within that there's a bunch of paragraphs. You'll see that? So here I did a search for a P tag. Okay, now we covered last week the rvest package. With the rvest package, we said if you load in the rvest package and if you load in dplyr, you don't really need to load in dplyr. It automatically loads in the background with rvest. The function we talked about last week was basically, or the steps we talked about last week was essentially first define a URL. So here I'm passing in the URL as the link to the economic sciences department. To actually go to the URL and extract all of the HTML that makes up the web page, this stuff, we can use the read HTML function. So R then just now went to the website, it downloaded all of the HTML and stored everything it collected inside of HTML content. And we talked about things like you can check the status, so you can do things like HTML _ content, $ status. Oh, whoops, that was the other word, sorry. That's with the GET request with HTTR. Nonetheless, here we can go into HTML content. We can use our little pipe operator from dplyr to extract all of the HTML nodes that have a P class. And then within there, we can extract all of the actual text. All right, so this is what I was hoping for you guys would be able to do. So your response should look something like this, right? The newly renamed Department of Economic Sciences provides research and teaching into 2 broad areas. And if we go here, the first paragraph tag is exactly that. The newly renamed Department of Economic Sciences provides research and teaching in 2 broad areas. You'll see that?
Yes.
No struggles there, right?
Can you go up where the name of the faculty starts?
Here?
No, in the RMD.
In the R Markdown file?
Yes.
So that's the next problem.
Line 7. Where is it?
That's the next problem. So the next problem I asked you to, so problem 2, I asked you to go to the actual web page and collect the names of all of the faculty members, right? So here I only wanted you to get faculty members because there's other names on some of the department's websites that are not faculty members. So like here there's a bunch of names. So here's Brian and Matthew, who are both administrative representatives. We don't really care about them. All I want you to get is actually the faculty members, which is all of us here, right? So if you use the inspect tool, you'll see that all of the faculty names are actually written in the same way. All of them are a header of class 4. So the header font basically defines how big the title is. And H1 is the largest, and you can go all the way up to H6, which would be like the smallest title. So here it's an H4 of this particular class. The class is u-nudge space u-weights-bold. Okay. All this class is it's really defining a style, right? So whoever built this website defined the style for an H4 to be nudge, weight, bold. So in another class or in another file called the CSS file, there's where they actually create a style sheet. And that style sheet contains things like what you're seeing over here, which is if the class is u-nudge, it's going to basically add in a margin on the top of the element of 0.75 or 0.75. Make sense? So all this class is doing is defining basically what type of object I really want to make this H4 to be. Okay. So what you would need to do in R, take this actual class, copy it, and here you'd be able to read in the faculty names. So here, actually here, the way I've written this is a little bit differently. So there's a couple ways you can do this. This first version that I'll show you guys is we go to the URL, the same thing. We read in the HTML content. You don't really need to do this twice. What you could do is just go into HTML content. Go into HTML content, find the HTML. Anwar, can you turn down your mic, please?
Oh.
There you go. Okay, so we can go into the HTML content. We can find the header of type 4 of a specific class. Okay, and this would extract for us all of the faculty names. So you can go into an H4 of this specific class and extract the actual text. Okay, that's one way to do it. Another way to do it is to actually recognize that all of the faculty names are actually inside of this container. See that? So there's this big container. Inside of this big container, there's a bunch of smaller containers, and each container contains a faculty profile. See it? Okay, why does that matter? Well, by just using this u-nudge, u-weight bold, I have a small problem. Specifically, the problem is I have Paul Zach twice. Okay, I have Paul Zach in here twice because he's shown here inside of core faculty. There he is. But he's also shown somewhere else. Where? There's Paul Zach.
At the top.
At the top, right here. Right? I think it's also then for, yeah, we have Graham Bird twice. We have Paul Zach twice. And we might have Greg twice as well. Right? So they're occurring twice because there's this section up top here where it basically lists the top or the three heads of the department, because right now we don't have one chair, we have 3 chairs for some reason. So here the code is extracting their names twice. So rather than just getting then all of the header class of type 4 of class u-nudge, u-weight bold on the website, what we can do is say, hold on a second, don't get all of them, only get the headers of type 4 inside of this particular divider, or inside of this particular area or container. Okay, so you can use your selector tool to narrow down this object. Okay, now we talked about selecting elements from an HTML page using its class. Right here, it's a div of class uClear. There's another way of actually identifying elements on a web page. And if you right-click on an object, you'll get this little menu. You can go to copy, and there's this thing called XPath. Okay, XPath essentially tells you where an element is inside of the the entire HTML structure. Okay, do you guys see how the HTML code here is printing out kind of like a tree structure? Kind of like a list, actually. Do you all see that? I have like some things inside of other things. It's all kind of nested, right? Okay, that's actually a format of data called XML. And you can actually copy and identify where something falls inside of this sort of tree structure using its XPath. Okay, so the XPath just shows you the path you need to take inside of the HTML to reach a particular element. Okay, so if you do copy XPath and you go into the code here, okay, you'll see what I just pasted is exactly the code I have already written here for the solutions I wrote up for you guys. Turns out in this HTML nodes thing, by default, it takes in the ability to look up and search for specific HTML tags. That's what we used up here. But it actually has this option where you can specify an XPath. Okay, so if you do question mark HTML nodes, you'll actually be able to read the documentation. Okay, and you'll see that you have basically the ability to look up things by their CSS value or the XPath. So there's multiple ways to identify something inside of a web page. But here we're just going to use the XPath. So basically we're saying, go into the HTML content, go specifically to this div, the fourth div. Then from there, get all of the tags that start with H4. From there, extract all of the text. So when we do that, we get the faculty names, which is just entered once. This makes sense? So this is basically the two ways to do this problem. You can just try and grab the generic all titles, or you can say, no. Go to this specific div. Within this specific div, find these specific tags. Make sense? Okay. Now, this next problem is kind of exactly the same thing, but I wanted you guys to explore basically not just getting things like actual text that's on the page. You can actually get other things like attributes. Okay, so at every single professor's profile, or at every single professor's little container that contains their information, right? At the bottom of it, there's this view profile thing. Yeah? Okay. View profile is a link. Okay. Specifically, see how here it says A.U font Mercury. Okay, A stands for attributed text. Basically, it's a way of embedding a link. It's like a hyperlink. You guys have used hyperlinks inside of like Microsoft Word or in an email. You paste in a URL, it automatically turns it into a link for you. All it's doing is making it an attributed text field. So basically, this text field isn't just text. It contains a path to a certain file or to another directory. Okay. The other directory here is basically that faculty member's webpage. So every single faculty member, right, including me, has a attributed text field inside of their own little container. And as I highlight it, you'll see CGU basically made for me a little web page. And the web page is https://cgu.edu/people/heysum-salbuni. You see that? Okay. So basically what we need to do is we need to go into all of these attributed text fields of class uFontMercury inside of this div that we identified a little bit earlier, and we'll be able to extract the links to everyone's profile. Okay, that's all that's going on here. So this XPath thing is exactly what we just talked about. Go to that main container where all of the faculty members reside. Now, rather than just getting H4 titles, find specifically A.U-font-Mercury, and then within there, don't get the text, get the HTML attribute of href. Href here, href contains the link to my web page. Make sense? Ami, am I losing you? Or am I going too quick?
Now, sir, it means you wanted us to go to each faculty, to
That's
the
the next part.
profile of each faculty. That's it?
Ami, you with me?
Yes, I'm here. Sorry, I didn't realize I was still muted.
No worries. Okay, so this would extract for us then all of the links to each of the faculty members' web pages. So there's Graham Bird, there's Greg, there's Robert, there's me, there's Tom Willett, there's Paul Zach, right? And all of us are entered once. There's no repetition. Okay. Now, problem 4, basically I ask you to just put everything you've collected together inside of a data frame. So all you need to do is create this thing called faculty DF. You can assign some column names like faculty and links. So then faculty DF looks like this. You have basically the faculty member's name that was collected in problem 2, the links that were collected in problem 3, problem 4 just puts it all together in a nice matrix for us. Okay, and then now problem 5, all you needed to do was actually use what you did in problem 1. Okay, by that I mean you create an empty list where you're going to store data. And what you're going to do is, here we have 10 different links, right? You're going to go to each of those links. So go to link 1. On link 1, so here's Graham Bird. He's link 1. If we click on view profile, we can see a description of Graham Bird. Okay, Graham Bird's description is inside of a paragraph tag. So what I asked you to do in problem 5 is go to each of those links you collected and grab all of the paragraph tags. That is, grab each faculty member's description. Okay, and store it inside of this object called store content. So there's a couple things going on here. One, there's a loop. The loop is saying for I in 1 to the number of rows of faculty DF. That is, I is going to take on a value of 1, 2, 3, 4, all the way up to n row faculty DF, which is 10. Okay, what are we going to do for each iteration? That's inside of the curly brackets, everything in here. Okay, I wrote out for you guys a function that I haven't shown you before. And that function is called try catch. Does anyone want to tell me what try catch is?
I saw online that it was basically something to replace error messages so that it doesn't stop running the code, but rather just like replaces it with some sort of message and then it just keeps going.
Perfect. That's exactly it. So try catch is going to try this first region of code. And if an error occurs, it's not going to stop the code. It's going to catch the error in the way you define how to handle it. Okay, so it's an error handling technique. And I've written, so like you can actually write, let's say, a different way of code. So here you could say, if the error is this, actually try this other method. And you can write your own little code there. But here, all I wrote for you guys is print the error. Okay, so it's not going to stop the code. It's going to keep going all the way through. And it's just going to print out whatever error occurs. Okay, now, whenever you're actually doing web scraping, you're going to want to use try catch because guaranteed not every web page is going to be exactly the same. So you're going to run into some errors. But if you're collecting like 10,000 pages of something, you don't want your code to stop every time an error occurs. You want to just go as far as it possibly can, then go back and diagnose whatever errors occurred on specific pages and extract the content from those specific pages. Okay, so it's just a way to error handle things. Okay, what are we going to try to do? We're going to try and go to each faculty member's link that we collected. See that? So we're defining URL. We're overriding it each iteration of the loop. We're overriding it with the ith link inside of the data frame we created before in problem 4. We're going to read the HTML from that URL. We're going to go into that HTML that we collected. We're going to extract the HTML nodes that are paragraph tags, and then we're going to get the HTML text. That is the actual text inside of those tags. And then we're going to store that paragraph content inside of the ith element of our list, which is outside of the loop. Okay. And then here I've written in a pause. The pause is going to sys.sleep. Sys.sleep basically builds in a pause into your code where it actually forces R to pause for a certain amount of time. So you define the time in seconds. The amount of time that we're going to pause that I've written here is basically randomly distributed between 5 to 10 seconds. So on average, 7.5 seconds. Okay. Remember how Atusa brought up an interesting point last week where actually if you query a website enough times, it's actually a form of an attack. It's called the DDoS attack. Denial of service attack. Yeah? Okay.
I remember.
Yeah, you don't want to attack a website, okay? And the way you can do that is by basically intentionally building in pauses into your code. Right? That way you're not overwhelming their server. You're going slowly like a normal user would if they were just interacting with the content. Okay. Then down here, there's going to be a print of I divided by n row faculty df that is just going to be a little progress bar for us. Okay, so if we run this, we'll get a little message. Okay, so 10% done.
Hey, Hassam, is there a way to put stops?
That's the sys.sleep, this part.
I mean, making the code like kind of like run through it one line at a time, or no?
Yeah, you can. So actually here, I'm going to stop my code. I can actually just define I is equal to 1. See that?
Mm-hmm.
And then I can literally just run that line. I can see what's going on. I can set I equal to 2. I can run that iteration. So I is actually a variable, right?
Okay.
Okay. I'm going to make this lag, right? Do as I say, not as I do. I'm going to make my lag a little bit quicker.
I was thinking more like stepping through the code. Like
That's exactly it. That's what I just did.
Yeah. Okay. But it looks like you have to do it with commands to step through the code instead of with, because you know in some language, like in VBA, you could actually put a stop.
Yeah, you can. So you can actually build in, so if you, in RStudio, if you double click on a line, whoops, you can add in, where is it? You can do view and debug.
Mm-hmm.
I'm pretty sure you can add a breakpoint somewhere here. Here, step into function.
Oh, got it. Okay, yeah.
So it's a debugging technique.
Thank you.
Yeah. So I just ran this loop. Now I have a list called store content. If I click on it, we'll see that there are a bunch of different elements in it. Specifically, there are length store content, 10 elements, 1 for each faculty member. So let's say I go into store content 4. That is the 4th element of the list. This is Debbie. If I go into the 6th element of the list, that looks like it's Tom Kniesner. If we go into the 7th element of the list, that looks like me. Okay, so we can see that we actually successfully collected all of the individuals' information. Okay, so this whole assignment was basically to give you practice. 1, just grab a generic paragraph tag. 2, extract information from one web page, then use that information to collect more information from other web pages inside of that website. Make sense? Ami, does this explain this last problem?
Sorry. It does. It especially explains like that set of numbers. I'm just trying to do the paste command thing.
This down here?
Yeah.
Okay. Do you see how here, You see how on, so let's say we go to my actual web page. Here it is, view profile. If I use my little inspector tool, I can see that this is a paragraph, right? So here's the description of me and where I got my PhD, where I got my master's, right? Down here, there's another paragraph tag. There's a couple other ones, right? The web page is, in the code we wrote here, we're actually grabbing all of the paragraph tags. We're not saying grab a specific paragraph tag. So wherever there's a paragraph tag, it's going to be its own separate element, okay? What this last paste command is doing is it's collapsing all of the elements. So here there's 2 elements, right?
Mm.
What this is going to do is it's going to collapse all of those elements by a space. By that I mean it's just going to merge those 2 things together into one element.
Okay.
So all this paste command is doing is it's collapsing multiple elements into just one element, one string.
One of the issues that I was having was when I tried to run the loop and grab the links from the data frame, it kept saying that it was reading it as a factor, even though you specified it as with the false. Even if I had that, it still said that it was reading it as a factor. So what I had to do is I had to go back and
you could coerce it. So you could do something like as.character.
Yeah.
That shouldn't be the case, right? If you did this.
I think it's because in your hint, string and factor, you misspell it. It should be strings with S.
Oh, you're right. I wrote string as factor. String. I think I made the same mistake last year when I gave this assignment.
Yes.
And you're the one that called me out on it last year as well. Thanks, Uni.
Okay. So I think that,
that's what it is. It's strings as factor.
It took me a while to get around it, but I couldn't see that the function was written incorrectly. So that was my mistake.
It's always great when the hint makes things worse.
I should have caught on to it.
That's my bad. Any other questions on this? Ami?
No, that looks good.
Artusa? Anyone? No, you're all good? Great. Okay. Now we're going to jump into lecture 8, which is on Canvas. And again, while we do this, please already start downloading QGIS and please already start downloading the census tract files. Okay, so we're going to get started inside of lecture 8. And you have a question?
Open QGIS file.
How do you mean?
Like it says I cannot open because Apple cannot check it for malicious software.
Oh, okay, gotcha. So when that happens, if you're on a Mac, so you might have like this DMG file, yes?
Yes.
Okay. If you click on it, it should open. If you can't open it, then what you need to do is, so you should have gone something like this, but if you don't get that, what you can do is actually open up the file. So like, let's say find it inside of a folder. If you right click on it, you can click open. Do that.
So I'm a little past that point, and in the sense that like I've downloaded, I uninstalled it and re-downloaded it, and now I have the app, but like I'm trying to open it and I'm double clicking and everything. No message. It's not opening. I try to force open it, and there's like nothing happening. I don't know if anyone's had that issue.
During the break, just share your screen with me, and we'll try and figure out what's going on.
Okay.
Okay. Right now, what we're going to get started with is lecture 8, which I've refreshed this morning. So please make sure you have the latest version of lecture 8, and that's where we're going to get started. Okay. So as I mentioned a little bit earlier, today we're going to spend some time talking about binary response models. Okay. So a binary response model is literally just the situation where your dependent variable can take on a value of 0 or 1. Okay. Now that you guys have covered sort of the basics of a regression, right, with ordinary least squares, you need to start thinking about the type of data you're working with to make sure that OLS is actually appropriate. Okay, so one example we're going to talk about today is specifically just binary choice models or binary response models. So a binary response model basically falls within a subset of a more general class of models called limited dependent variable models. So basically what we're going to be working with today is in one of the last chapters of your book, chapter 17 of Oldridge. And in there, they cover a few more models as well that deal with types of data that are censored or count data. There's basically certain types of regression models you can deploy to fit certain types of data. Okay, so like imagine you're dealing with count data. You can use a regression, but remember how we talked about like the predictions for the student to teacher ratio? Remember how we said the domain of that regression is going to be from -infinity to +infinity? And you're also getting like continuous test scores, like you can predict the score is 16.74 or something. When in reality, a score may just be integers. It could be 16 or 17. There is no 16.74. Okay. There are certain types of regression models you can deploy. For count variables, you would use something called a Poisson regression to address that certain type of data. Right now, we're just going to focus in on the special case where your dependent variable is a 0-1 outcome. Okay, and you can think of these 0-1 outcomes as, here's a couple examples for you. Maybe you're interested in trading. You want to figure out what's the likelihood of a stock price increasing. If it goes up, we'll call it a 1. If it goes down, we'll call it a 0. Okay. Maybe you're interested in crime. So you're a judge and you have historical data on an individual. Maybe you try and predict what's the likelihood of this person recommitting a crime if I release them. Okay. They recommit, that's a 1. They don't recommit a crime, that's a 0. Okay, and you can easily imagine a historical sample of data where I have data on people, I released them, and I record what actually happened. If they ended up recommitting a crime, I'll flag them as 1. If they didn't end up recommitting a crime, I'll call them a 0. And then I can analyze basically what were the characteristics of those people as my explanatory variables. Okay, with the crazy things we're seeing in employment right now, right? We had another 4.65 initial unemployment claims last week, so we're up to 26.5 million people filing for unemployment in the past month, basically. You could basically come up with a model to try and predict who's getting fired, right? Is a person in the workforce? That could be coded as a 1. If they're not in the workforce, that could be coded as a 0. Okay. So basically what we're going to try and do is we're going to try and build a model that can help us explain a binary variable of interest. That is, what causes a stock price to go up versus go down? What causes a person to recommit a crime? Or what are the characteristics of someone who's likely to recommit a crime? Similarly, what are the characteristics of someone who's in the workforce or not? And by characteristics, you can really think of this as like y equals x times beta format. The x's are the characteristics, right? Those are explanatory variables that are trying to explain what's happening with our dependent variable. Okay. Now, what I'm saying sounds really fancy. In reality, you can actually just deploy ordinary least squares. Okay. But if you use ordinary least squares, we change the name. So if you're using ordinary least squares where you have a dependent variable that is binary, that takes on a value of 0 or 1, that is your y is a 0 or 1, we call that a linear probability model. Okay, so a linear probability model is just ordinary least squares. I don't want you to think it's anything else. It's ordinary least squares, but your dependent variables are 0 or 1. It's just a basic regression. How many of you have seen these sort of models before in a paper or in some of your past work?
If you have a model that one of the variables is binary, would that be the linear probability, or is that just a regular OLS with one of the
Where your dependent variable is binary?
one of them?
What do you mean one of your dependent variables? There's only one dependent variable. Your y.
Oh, got it. Okay, never mind.
Okay.
Independent. I mean, you're
independent. That's just a dummy variable or a category.
Yeah.
You can have as many of those as your heart desires. So we're going to see that a little bit later. Okay, so when your dependent variable, the y, the thing you're trying to explain, is a 0 or 1, we call that a linear probability model, if you're just using OLS. Okay, ordinary least squares is not the only way to estimate these sort of models. Okay, you can use ordinary least squares to estimate a 0 or 1 outcome variable. You can use a logistic regression. You can use a probit regression. You can use decision trees. You can use boosted decision trees. You could use random forests. You can use deep neural networks. There's tons of models that you can deploy in the machine learning space in particular to try and explain categorical variables or 0 or 1 variables, okay? When your dependent variable is 0 or 1. Okay, we're going to focus on 3 models today, which are the most basic ones. Linear probability model, which we're going to use to build the foundations because we already know how to use OLS pretty damn well. Then we're going to discuss a logistic regression and a probit regression. Okay, so we're going to get started with just our good old linear probability model. Let me get the PDF open. It'll be easier to see that. Okay, our linear probability model is exactly the same thing as OLS. It's literally nothing is different, right? Y equals x beta plus epsilon. Here, x is my set of independent variables. That is the things I want to try and explain what's causing my binary variable to take on a value of 0 or 1. Beta is my vector of coefficients, the weights I want to assign to each of my different independent variables. Epsilon is my error term. Okay. Now, when we're running a regression, what we're really doing, right, is we're taking the expectation. Essentially, what we're doing is we're taking the expectation of y conditional on x, right? That's all we're doing in a regression. We're taking the expectation of y conditional on a set of explanatory variables or conditional on x. When we're thinking about expectations, we have to think about the structure of our data, okay? If our dependent variable is taking on a value of 0 or 1, it's essentially just a Bernoulli random variable, right? A Bernoulli random variable is just a variable that takes on 2 outcomes, 0 or 1, right? Yeah? Okay. Well, using the fact that it's just a 0 or 1, using the fact that it follows a Bernoulli distribution, we can use the properties of Bernoulli random variables to try and come up with how we analyze the expectations of that dependent variable. Okay, right? In general, the expected value of a Bernoulli random variable is literally just the probability weighted average of that random variable being successful or not. That is, the expected value of Bernoulli random variable x is just the probability of observing a successful trial of x, that is x equal to 1, times the outcome if that occurs, 1, plus the probability of observing a failure, or x equal to 0, times the outcome at 0, which is 0, which is just equal to then the probability of x equaling 1. So the expected value of a Bernoulli random variable is really just equal to probability of being a 1. Make sense? The reason why this matters is here we're running a regression where we're taking the expectation of y conditional on this equation. If we treat y as a Bernoulli random variable, the expectation of y is going to just be the probability of y equaling 1. So by just having a dependent variable that takes on a value of 0 or 1, the interpretation of our regression becomes, that is, the fitted values of the regression end up just literally giving us the probability of us observing a 1 or a 0. So that is, you run a regression, your dependent variable takes on a value of 0 or 1, you're going to plug in your x's times your betas, you're going to get a number. That number is going to be interpreted as the probability of y equaling 1. Right? And vice versa, 1 minus that probability is the probability of y equaling 0. Right? That's all that we've written here. Am I losing you guys, or are you with me?
We're with you.
Makes sense.
Thank you. And thank you. All right, that's 2 out of like 20. Annie, Atusa, Ami, here's the names I see on my screen.
Yeah, I'm going to ask you to repeat that one more time. I'm sorry.
No, good. See, say something. It's okay. Okay. Whenever we're dealing with a Bernoulli random variable, by that I just mean a variable that takes on a value of 0 or 1, the expected value of that variable is just the probability of you observing the 1. For instance, let's say we're talking about flipping coins. Okay. You flip a coin. If it's heads, we'll code it as a 0. If it's tails, we'll code it as a 1. Okay. You flip the coin a bunch of times. You get a bunch of zeros. You get a bunch of ones that you record. Right? If you take the average of the zeros and ones, the expected value of all those zeros and ones, with a fair coin, you'd expect it to be 0.5, right? That 0.5 is a measure of the probability of x equaling 1, or in this case, the probability of observing the coin being tails. Does that make sense, Ami?
Yes.
Good. Actually?
Yes.
Okay.
Actually.
Don't be shy. Okay. I think the easiest way to see these sort of models is to actually walk through an example. Okay. And by doing an example with actual data, we'll be able to start deploying our robustness checks that we covered as well for ordinary least squares. All right, we need to make sure our Gauss-Markov assumptions hold. Because a linear probability model, we said, is just ordinary least squares. Well, if it's just ordinary least squares, we need to make sure that we're following the Gauss-Markov assumptions. Okay. So what we're going to do is we're going to use some data on home mortgage applications. Right. So in the United States, typically when you buy a home, people don't usually have the cash to buy the full value of the home. So what they do is they put a down payment. Let me do some drawing because I know mortgages aren't necessarily a familiar thing all over the world. New share, iPad, Zoom. There we go. Whiteboard. Okay. So in the US, right, you want to go buy yourself a nice little home. That's my beautiful drawing. You want to go buy a home. Let's say this home, this little shack in Orange County will cost you $1 million. Okay. And let's say after, several years of hard work, you saved up a very substantial down payment of $200,000. What you can do in the United States is you'll put the $200,000 as a down payment. You'll borrow $800,000 from the bank. Okay, so mine, bank. Okay, this amount from the bank is called a mortgage, right? And basically what you'll say is, hello, Mr. or Mrs. Banker, can you lend me $800,000 to buy this home? I'll make a payment to you every month for the next 30 years to pay back this $800,000. Okay, and if I don't pay it back, you can take my house. All right, seems like a good deal for them. Okay, this is called a mortgage. And the way these mortgages typically work is you have to apply for them. So you go to your banker and you tell them, well, I want to buy this house. I'm going to put down a down payment of 20% in this case. So this is called a 20% down payment. That's the money I'm putting up front. I tell them the value of this house was appraised by a real estate professional who specializes, and they told me the value of the home is $1 million, right? Which means that I want a loan of $800,000. Okay. The bank will say, okay, sure. I need some more information about you. What's your current income? What's your current debt that you have outstanding? And they'll even ask some odd questions like, what's your ethnicity? Okay. Or maybe
Why do they ask that? Out of curiosity.
no idea. Okay. Well, technically, they're not legally allowed to ask. So we'll be clear about that. But what we can do is we can keep track of people's ethnicities if they go to the bank and see what their mortgage application looks like. Okay, so they fill out all of this stuff. This isn't necessarily, is not going to be recorded by the bank. It's illegal for them to do that. Okay, but what we can do is control for people's ethnicity. Let's say 0, is there anything? 1 is African American. Okay, so 0 is everyone else. Okay, so we can say someone is 0 means everyone else, so 1 means African American. Okay. What we can do is we can actually try to build a model where we can go back through historical loan applications and we can see whose application was accepted and whose application was rejected. Okay, so we can make our, right, we're going to set up a regression in the same format as always. Y equals beta 0 plus beta 1, x1 plus beta 2, x2 plus a bunch of stuff, right? Our y variable in this case is going to be a 0 or a 1. 0 could be loan rejected. 1 could be loan accepted. That is, the person filled out all of this information, they submitted it to their banker, and the banker says, great, we're going to fund your loan. Or they'll say, no, we're not going to fund your loan. Okay, same thing like going to buy a car. You apply for financing. You could get accepted or you could get rejected. Right? Now, what are some reasons why you might get rejected? Well, if you have a very low down payment, you might get rejected. If you have a very high amount of debt, you may get rejected. If the loan exceeds the value of the home, you may get rejected. That is, I go to my bank and tell them, hey, I'd like a $1.2 million home for this $800,000. I'd like a $1.2 million loan for this $1 million home. They might say, no, sorry, that's not going to fly. That actually does happen though, right? Maybe I want to take out a loan on the house and also I want to take out a little bit more money to do some renovations on the home, which you can actually do. Okay. all of these things are potential explanatory variables or potential independent variables to try and explain why a loan can get accepted or rejected. And that's also a great thing. A credit score, right? So if a person has bad credit, that is, they have a bad history of repaying their loans, I may reject them, right? Okay. There could be some other stuff as well. What industry does this person work in? Is there a very seasonal unemployment in this sector? Okay. These are all things that a person working at a bank would try to build a model to see who they should accept and who they should reject in order to minimize the risk of their loan pool. Okay. So we can actually then try and build a model for something like I've written in a lecture, where we might have our Y is were they accepted or rejected. So we can say our new dependent variable is mortgage accepted. Okay, we'll add an intercept term. We may add in then some explanatory variables like what's their payment to income ratio. That is, on this $800,000 loan, we can figure out what the payment is with the interest and the term. Is that going to be too high of a payment relative to this person's income? Because if it's too high as a proportion, right, like let's say your mortgage is 80% of your income, you're probably going to default. You're not going to be able to actually make the payments on your loan. Okay. What's the loan to value ratio? Right, and this tells us basically all. So this variable loan to value contains a lot of information. It tells us about basically the debt to equity mix of the home. How much is the person actually putting down versus how much are they financing? Okay. We may have an additional term. What's the unemployment in this person's sector? We may have another term. That is, what's the person's ethnicity? Are they African American? Now, we would hope that beta 4 is statistically not different from 0. We don't want beta 4 to be positive, and we don't want beta 4 to be negative, right? We don't want black people to be getting special treatment, and we don't want black people to be getting unspecial treatment. We want to have people treated as people, how they should be treated, right? Yes.
In the beta 3, like unemployment sector, we are considering like stability of that sector.
Exactly. Right. So we don't want maybe if someone works in some seasonal job, like certain construction jobs are seasonal, right? I mean, not in California.
So it's about sustainability of his employment.
Yeah, so if one sector is very seasonal, right, that means they're going to have times during the year where they have high unemployment and low unemployment. So on average, it's going to be pretty high, versus a desk job may have low unemployment over time. Okay. So what we can do then is we can actually estimate this model if we have some data. Fortunately, we do. Okay. Now, because our dependent variable in this case takes on a value of 0 or 1, what we're really estimating by this equation is, given all of this information about an individual, what is the probability of their application getting accepted? Okay, so what is the probability of the mortgage getting accepted conditional on X, where X is all of this other crap we're controlling for? Okay. Let's get some data, and then let's just see what comes out of the model, okay? It'll be a very natural way for us to see the assumptions we're making in this model, and we'll be able to basically then talk about, do they make sense or not? Okay. So let me jump back into R. Okay. We're going to be using that applied econometrics with R package again. So you need to load that in. If you don't have it, you can do install.packages and then in quotes AER. Okay, but you should all have it at this point. So if you do library AER, actually I'm just going to clean up my workspace real quick. So if you do library AER, that should load in the package for you. We're going to be using a data set called HMDA. And you can attach that data set by using the command data and then the name of the data set HMDA. If you do $HMDA, you'll pull up the documentation. Okay, so here it is. It's the Home Mortgage Disclosure Act data. Okay, so this data set contains 2,380 observations and has 14 variables. There's a deny variable, which is a factor, and it tells us was the mortgage application denied. We have PIRAT, P-I-R-A-T, which is the payment to income ratio. You have HIRAT, housing expense to income ratio. LVRAT, loan to value ratio. We have the variable for credit history, for mortgage payments, for public bad credit record. We have the unemployment rate. And we have a variable for if the person is self-employed or not, because self-employed people they get fired, right? Crappy boss. They have insurance on the mortgage. Is it a condominium? And then here we have basically, is the person single? Because maybe if they're married, you have a dual income. Does the person have a high school diploma? So we know about their education. And then also, is the person of African-American descent or not? And so we have lots of data here. Okay. What we're going to do is, if we take a look at the structure of HMDA, so if you just do head HMDA, you can preview the data set, right? And here's all of the data. Okay. Here we can see that there's a variable called deny. Right? Deny takes on a value of no if they're not denied, and a value of yes if they are denied. Now, in the specification we just wrote up together, I actually have the opposite of this. My dependent variable was accepted. What's the likelihood of someone getting their mortgage application accepted? Not rejected, accepted. Okay, this is important. The way you code up your dependent variable is going to define the way you interpret the model. Okay, if we use deny as our dependent variable, we're going to be estimating the probability of your mortgage application getting denied. That is, deny takes on a value of 1 if you're denied, and a value of 0 if you're not denied. We said with a Bernoulli random variable, you're estimating the probability of a success, the probability of a 1. So depending on what you define as 1 is going to be the way you interpret the model. Make sense? Okay, so rather than looking at the likelihood of someone getting denied, let's say I want to look at the likelihood of someone getting accepted. That is, what are the characteristics of a successful applicant? So what I can do is just reverse the definition of deny. If HMA, the deny column, so inside of the HMDA data set, inside of the deny column, if that is equal to no, this is going to return true. If it's equal to yes, it's going to return false. So we're reversing the definition of no's and yeses. No's become trues, yeses become false. You see that? Remember, double equal sign is doing a logical check. Is this thing equal to this thing? And we're creating a new column called accepted, which is going to store the results of that. So if we do head HMDA again, we'll see there's this new column called accepted, which is true, 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 which means all of these people have their mortgage application accepted. Any questions on this? Good. Ami, Atusa,
Looks good.
Dafta, good. Dana, you good?
Good.
Okay. All right. So one of the useful commands that, or one of the useful things to always do is to just summarize your data set, right? What's the data structure we're dealing with? Okay. One of the useful commands we've used before is this table command. Remember, table is going to go through and give you a frequency count of the number of times something occurs inside of a vector. So here, we just created this new vector, accepted. It has trues and falses inside of it. If we do the command table on that accepted column, it'll give us the actual counts. How many falses are inside of the data set? How many trues are inside of the data set? So here we have 285 entries are equal to false. 2,095 are equal to true. So the vast majority of applicants are accepted. Now, rather than looking at just the pure counts, I can divide by the total number of observations I have, and that'll give me the percentage of those rejected versus those accepted. So here it's saying 11.97% false, rejected, 88.02% accepted, true. Okay. Now, right off the bat, we can do some very simple things. We can look at, for instance, what is the PI-RAT, if I look at my documentation, payments to income ratio. How does the payment to income ratio differ for people that were accepted versus rejected? One way to summarize data is using a box plot. Okay, so a box and whisker plot. If we plot this out, we'll get this little graph here. Okay. False is this category, true is this category. That is, this group of people had their mortgage application accepted. This group of people had their mortgage application rejected. Okay. Now, the way a box plot works is this line here and this line here. So there's a bottom line and a top line. You see those? That basically covers the 1 percentile and 99 percentile. These dots up here are like major outliers. Okay. The boundaries of the box from here to here cover the 25th to 75th percentile of the data. Now it's hard to see in here, but there's actually two horizontal lines inside of this box. One is the median, one is the mean. Okay. I know it's a bit difficult to see here, but what I want you guys to focus on is, see how the middle line of the box is higher here than it is here? This is above this. See that? Here it's telling us people that have a higher payment to income ratio, that is, their monthly payment on the mortgage makes up a higher proportion of their income per month, are likely to get rejected. The lower your payment to income ratio, the more likely you are to be accepted. Intuitively makes sense. Okay. Another thing we can look at is the loan to value ratio. Okay. Same thing again. The loan to value ratio. As the loan to value ratio is declining, there's a higher chance of you getting accepted. Think about it. $1 million house. If you're taking out a loan for $999,000, your loan to value ratio is basically 1. That's way up here. If instead your loan is $100,000, your loan to value ratio is down here.
Yeah, it represents the strength of the collateral.
Exactly. How much money are the people putting down? the more the person is putting down, the lower the loan to value ratio.
Yes.
I have a question.
Yeah.
About the outliers on that. So that on the right side, we see that there's a lot of outliers that have been accepted, even though they have higher ratios.
Mhm.
Oh, okay. But on average, but the average is lower compared to the other one.
Yes. So this can occur. So, I mean, you have to like work in the industry to know, right?
Yeah.
Why could this ever occur? One, could be an error. They typed in the data wrong. Two, it could be that this is a very, very, very high net worth individual and they have a huge number of assets. So they're just allowing the person to take out a bigger loan than the value of the property. Or it could be something like it's a mixed loan. That is, you're buying the value, let's say you're buying just a plot of land, but you take out a loan for the land plus a construction loan. Right? You need really the more like details or like to understand the actual intricacies of the loan, but here we're just abstracting, right?
Makes sense. It just kind of threw me off a little bit.
Yeah, it should. It's weird.
Another scenario, another reason is that maybe they are targeting, like now we are going to the election, they are targeting the low income people who are many and they have many votes. And those who are rich, they are very few. So their votes are very few also. So it depends on the purpose of the loan. That may be also another reason.
Yeah. So it's basically going to come down to what is the lender's objective, right? So during the 2005 financial crisis, like during the 2008 financial crisis from 2005 to 2008, right? None of this stuff mattered. They were just giving the loans to everyone because the bank was just passing the loans along to an investor, where it was sticking everyone's loans together and then became diversified. Okay. So here we have a dependent variable accepted, takes on a value of 0 or 1. 0 is false, true is 1. We can try and explain the 0s and 1s conditional on a bunch of other stuff. Okay, so we can run a linear probability model. That is, what's the likelihood of an individual's mortgage application getting accepted, conditional on their payment to income ratio, the loan to value ratio, the unemployment of this individual's sector or industry that they work in, and the ethnicity indicator. Is this person of African American descent or not? We can estimate a linear probability model using the same LM command we've been using. It's just a linear model. So we can use LM, linear model. Accepted is our dependent variable, regressed on all of these things inside of the HMDA data. Okay, if we run that, this is our regression output. Okay, beta 0 is 1.249. How do I interpret this coefficient here? Okay, African American descent takes on a value of 1 if the person is of African American descent, and a value of 0 if they're not of African American descent. How do you interpret this coefficient here?
Would you say that it will reduce your chances of getting accepted by 16%?
Exactly. That's exactly it. Okay. Let me write up this model for us so we can walk through the details of how to interpret it. Okay, so our estimated model, is, was the mortgage accepted? Is equal to 1.24 hat minus 0.50 hat payment to income ratio minus 1.99 or 0.199 loan to value ratio minus 0.008 unemployment minus 0.165 African American descent. Okay, that's our estimated model. The way we interpret the model is exactly the same way we've been doing so. Basically, what is the partial effect? If we take the derivative of mortgage accepted with respect to, I don't know, payment to income ratio, that's going to be minus 0.5. That is, as payment to income ratio increases by 1 unit, say it goes from 1 to 2, which would be huge, right? There's a 50% decline in the likelihood of getting accepted, okay? In order to actually interpret it, we need to figure out what the scale of this is. So it's basically saying the change in the mortgage, the likelihood of getting accepted is equal to minus 0.5 times the change in the payment to income ratio, right? So if my payment to income ratio, let's say was 33%, that is, let's say I make $10,000 a month and my mortgage is $3,300 a month, 33%, okay? If I went from 33 to 34%, let's say my income went down a little bit or my mortgage payment went up a little bit, there is a 0.01. There's a 1% or a 1 percentage point increase in the payment to income ratio, right? Okay. That 0.01, you can multiply by minus 0.5 and it basically tells you a 1 percentage point increase in payment to income reduces the probability of mortgage accepted
By 50%.
by
50%.
5%. It'd be 0.01 times 0.5, which is 0.05 or 5%. That's pretty cool. If my payment to income ratio goes up by 1 percentage point, it reduces the likelihood of my application getting accepted by 5%. That's pretty huge.
By 5% or by 50%?
5%. You have to take, so it's 0.01, it's the change, 0.01
Yes.
times
And then,
minus 0.5 equals minus 0.05, which equals 5%.
okay. Oh, yeah.
See that?
Yes. That's it.
That's pretty cool. Okay, now, our model here is estimated with ordinary least squares. Our specification, by definition, is imposing linearity in the parameters. Okay, what that means is, if my payment to income ratio goes from 33% to 34%, that's going to reduce the likelihood of my mortgage getting accepted by 5%, right? How about if I go from 56% to 57%? still a 1% change, right? So it should still be 5%. Annie, isn't that 0.5%? I don't know, am I being stupid? Let's see. 0.5 times 0.01.
It's
Annie is,
0.005.
it's 0.5%.
Yeah.
1%, yeah.
Thanks, Annie. Okay, so every 1 unit change, right? It's good to, it's like when you're nervous on an exam, right? And you're just like 2 times 2 is 4, just to be sure.
1%, yeah.
Okay, so actually a 1 unit increase or 1 percentage point increase in my payment to income ratio reduces the likelihood of my mortgage getting accepted, not by 5 percentage points, by 0.5%, which is still pretty big. Okay, nonetheless though, what I've written here, is this correct?
I mean, it assumes that it's a constant change, right? Regardless at the where you find
Regardless of the level.
Right.
Okay, this is a weakness of these models. Okay, that's one weakness. This is going to be a weakness we're going to try to address in some nonlinear models like logistic regression and probit regression. In those models, actually, the marginal effects actually are going to vary depending on where you are across a bunch of dimensions in the sample. So that is, the partial effect can change depending on the individual. Okay, so this is going to be a weakness of the linear probability model. You have constant partial effects. It doesn't matter if you're going from 33% to 34%. It doesn't matter if you're going from 56 to 57%. It doesn't matter if you're going from 90% to 91%. You're just going to always, every additional 1 percentage point step you take, it's going to reduce the likelihood of you getting accepted by an additional 0.5%.
if you wanted to, or if you included that as a square, like a quadratic, like will that?
You can induce nonlinearity that way. Okay. Let's share desktop. Okay. So that's one thing. The coefficient on African American was correctly interpreted before. It's basically saying if someone is African American, there's a 16% chance of them getting their application, 16% higher chance of them getting their application rejected. Holding constant everything else, right? So 2 people are exactly the same house, same payment to income ratio, same loan to value ratio, same everything. Even with that, if they're African American, they have a 16% chance of getting their loan application rejected. Now, we know from some of the previous work we did, if our model has omitted variables, that is, maybe being African American correlates to something else. Maybe it's being correlated to just a different neighborhood, right? So here I gave the example of it's a similar house. It's not really a similar house or the same house. It could be that if you're African American, you choose to buy a home in one area. If you're of a different ethnicity, you choose to buy a home in a different area. Because of that, we could be measuring some form of discrimination that's not actually there. It could just be that the area they're buying the home in could be riskier, for instance. Right? So there could be some hidden or omitted variables from our model which could be causing us to have an incorrect estimate. Right? We saw that really clearly with the student to teacher ratio example. By including the percentage of English speakers in our model, it cut the size of the coefficient in half. Right? So I'm not saying there is no discrimination. I'm saying here we're measuring there is some discrimination. But our measurement, we should be aware, could be susceptible to omitted variable bias. Right? So it's just a model. And this model is telling us there is some discrimination, and it's a very statistically significant correlation. Okay. Now, the habit that we've been building is after you estimate a model, you interpret it, you interpret the coefficients. And then if you want to actually diagnose the model, you need to look at the residuals, right? Why do we need to look at the residuals again?
To look for the presence of heteroscedasticity.
Bingo. I need to know where these standard errors come from. I need to know if these standard errors are correct. Because we said under the Gauss-Markov assumptions, we're imposing, so basically under the reported baseline standard errors that come out of R or any statistical language, it's imposing homoscedasticity on the variance covariance matrix or the residuals. That is, they all have the same variance. You're making the same errors. There's no systematic error or grouping of error depending on the observation. Okay. Now, the easiest way we said to actually diagnose this was to extract the residuals of a model squared and take the fitted values of the model and plot them against one another. Okay. If we do that, we get this plot. Okay, again, our x variable, our y hat, or sorry, our x-axis here is our fitted values. That is the predicted y given the x's. It's our y hat. Yes? It's our fitted value. So this is what's predicted by our model. Here we have our, along our y-axis, the residual squared, the error. That is the difference between what we predicted and what actually occurred for that observation squared. Does this look like homoscedasticity to you? No. Right? What does homoscedasticity look like again? Constant variance. Here it looks like we're making very wacky errors. Here it looks like we're not making any, right? It looks like there's very little error in this domain, but then there's lots of error in this domain, and it's drastically different, right? For some observations, we're greatly underestimating. For some observations, we're greatly overestimating. Small error, big error, right? Small error, big error. It should be constant error. We should be making errors in the same way. That's what homoscedasticity is. Okay? That's one. Two, here I've drawn on this graph using this AV line command, two vertical lines. I drew a vertical line at 1, and I drew a vertical line at 0. This is the predicted values of our model. That's our x-axis, right? This is what's predicted by our model. Now, when we started, I said, what we're doing here is we're estimating the probability of a mortgage application being accepted conditional on all of our x's. The probability. Here we have some predicted values from our model that actually exceed 1. And some predicted values that exceed 0 or fall below 0. Remember how I said in a linear in ordinary least squares, you're predicting over the entire domain from minus infinity to positive infinity? That doesn't change when you're using a linear probability model. It's still ordinary least squares. You're still fitting a line. You're still fitting a plane through multiple dimensions, right? Because of that, the predicted values can exceed the 0, 1 range. Is that a problem? Is it a problem for the probability of something to be less than 0? Is that possible? Is it possible for the probability to exceed 1?
Does that even make any sense? How do we interpret that?
You can't, okay? But basically what you can do is you can just censor your results. So you can censor your predicted values and say, if it's greater than 1, just make it 1. If it's less than 0, just make it 0.
I have a question.
Yeah.
Would regressing through the origin make any difference here? So
that could cause lots of other issues. So if you force the intercept to be 0, right, then you run into the entire other problem of the mean of your residuals isn't necessarily 0 anymore. That's not going to fix anything. It could potentially help because you're making it say the average probability is 0, conditional on anything, or conditional when everything else is 0, right? That's going to bias your model.
thank you.
Yeah. But basically the model we fitted it starts off really high, right? So if we go back to our actual coefficients, so clear all drawings, close this. If we go back to our estimated coefficients, our intercept's actually bigger than 1. Right, so we're starting off with this high number, and then as these features change about, or as these independent variables change for an individual, we're basically reducing the likelihood. All of these are negative. We're reducing the likelihood of someone getting accepted, which makes sense. As your payment to income ratio goes up, it should reduce the likelihood of you getting accepted. As your loan to value ratio increases, it should reduce the likelihood of you getting accepted. As unemployment goes up, it should reduce the likelihood. This last one, that shouldn't be the case, right? But this is what the data is picking up. Make sense? Yes.
Makes
No?
sense.
Okay, thank you. It's one person, makes sense too. Okay, so whenever you're dealing with a linear probability model, you're going to have heteroscedasticity. It's pretty much a guarantee. And we can actually walk through a proof to show you why that's the case. Now, because I want to cover a lot of stuff, we're going to go through this proof pretty quickly, but that doesn't mean you're not responsible for knowing it. Okay. If we open up the PDF again, it's actually a pretty simple proof. If we think about the structure of our error term, essentially our errors can only be two things, right? We have epsilon, it's the error term, the residual. The error can only be minus x beta if y is equal to 0. Okay, I want you to think about it like this. Wish I could share both screens at once. Actually, here, I'll just annotate this screen. Our model, right, is y equals x beta plus epsilon. Yeah, that's our model. Okay, if y is 0, then epsilon equals minus x beta. If y is 1, then epsilon is equal to 1 minus x beta. Does that make sense where this is coming from? Francis, is that clear?
Yes, sir. I can see.
Okay, that's how we're making our errors. Now, because we're imposing an intercept term in our model, we know the mean of these residuals of this error term by definition is going to be 0. Right? It's just one of the nice properties of ordinary least squares. So if we were to then look at the variance of our residuals, the variance is just going to be the residuals squared, right? Because the mean is 0. We don't have to subtract anything out. It's just the variance is just fluctuation around 0. The average is 0, right? Because variance is squared dispersion around the mean. Okay. Well, when we're dealing with a Bernoulli random variable, basically the variance is just a probability weighted variance. That is, this is the variance minus x beta squared when, that is epsilon squared, when y equals 0. So we weight this likelihood. What's the likelihood of observing a 0? And the variance of getting a 0, plus what's the likelihood of observing a 1 times the variance if it's a 1, right? And that's coming from up here. So if we observe a 1 with this likelihood, this is the variance, epsilon squared. If we observe a 0 with this likelihood, this is the variance. Now, in our model, because it's a Bernoulli random variable, we know if we're assuming that our model doesn't have any omitted variable bias and is specified properly, then the probability of observing a 1, y equaling 1, is just equal to x beta. That's by definition, right? That's the expected value we wrote up earlier. So the variance of epsilon conditional on x, which is up here again, if you just plug in for the probability of equaling y is equal to x beta, and the probability of equaling 0 is 1 minus x beta, you end up with this term. Okay. The only thing I really want you to notice here is one of the core assumptions of ordinary least squares was the expected value of epsilon conditional on x was 0. And the variance conditional on x had nothing to do with x. You remember that? Here, we're violating those assumptions of ordinary least squares. Our variance of the residuals is directly related to our explanatory variables. So depending on the x you plug in, you're going to get a different error. That by definition means you're making errors in a systematic way depending on the x's, depending on the variables you're plugging in. So the quick workaround is just plug in the robust and consistent estimate of the residuals in the sandwich estimator and just use your good old white standard errors. Exactly the same way we did before. Okay, so here is our point estimates now using the robust standard errors. So it's going into the sandwich package. Now that you guys know how those are actually written up and you know how to even code them up yourself, right? You can just use the built-in VCOV HC that is derive the heteroscedasticity robust covariance matrix of the residuals, square the, use the sandwich estimator to get the variance and then plug in for the variance covariance matrix, just the square of the residuals with everything else 0 off the diagonal. Okay. Using those standard errors then, we can see that the coefficient on African American is still very significant. Okay. So our model could still be suffering from omitted variable bias. This is just assuming that our model is properly specified. If we use the correct standard errors, we're saying there's still a very significant effect, a very significant negative effect, being African American on having your mortgage accepted or rejected. Again, just to really make it really crystal clear, whenever we're making these corrections to the standard errors, it's never going to change the point estimate of the coefficients. That's going to stay the same. The interpretation stays the same. That's why we were able to do the interpretation before we did this part. But to actually see if it's a statistically different from 0 result, that is, there's actually an impact there, you need to have the correct standard errors. Okay? Now, when we're dealing with these sort of models, we can actually do a lot of other stuff too. we can evaluate these models in an entirely new dimension compared to a standard regression model, right? We talked about some things like adjusted R² before when we're dealing with a regression. You can still do that here. We talked about things like root mean squared error. Remember how we did a proof for the bias variance decomposition for root mean squared error? Okay. When you're dealing with a binary response variable, you can actually do a couple more things that are pretty cool. Now, our dependent variable takes on a value of 0 or 1, right? In our case, 1 if accepted, 0 if rejected. Yeah? If we look at the fitted values of our model, the fitted values we said, right, y hat is the probability of accepted, right? And this is a number, right? Like 0.6, 60% chance of getting accepted. 0.1, 10% chance of getting accepted. 1.2, 120% chance of getting accepted. Minus 0.1, minus 10% chance of getting accepted. Okay, I'm using those examples again to remind you that a linear probability model can predict outside of the 0-1 domain. What we can do though is just use a very simple decision rule. If we're predicting anything greater than 0.5, right, here's 1.1, here's 0.93, here's 0.84. If we're predicting anything greater than half, if else. If this number is greater than 0.5, code it as a 1, otherwise code it as a 0. So predicted acceptance now just takes on a value of 1 and 0, depending on if the probability of getting accepted is over a certain threshold. Okay. A generic version is using 0.5. Is that necessarily the best way to go? Anyone? What other number can I use?
It depends on the variable you are making decision on, because in the banking industry there is this so-called diversification ratios. So there is one which is what you call credit concentration limit. So like the one we have been saying, maybe being an African American, you have a little chance of getting accepted. The issue is not discrimination there. The issue is concentration limit from the regulator. Maybe this kind of groups, you know the principle that says you cannot have all eggs in one basket, that can apply here. So there is a limit.
Sure, but that's pretty unlikely in this case because the markets here are huge, right?
Yeah. But in the industry, that's one of the reasons.
Sure.
I think that there might be a couple of issues with like cutting the threshold of that, because like what if you're, at 49%, right? And, you'll basically get rejected right off the bat, like, without any more knowledge. It's like, hey, like if you were just to do this, improve this by 1 bit, you will be
accepted. So there's a couple things you can actually do. Instead of using 0.5, one thing you can do is, what's the average in the sample of someone getting accepted or not? If you do mean HMDA accepted, there's an 88% chance of you getting accepted, not controlling for anything, right? Just simple average. There's, holding everything blank, right? There's an 88% chance of you getting accepted. What if I plug in 0.88? That's another decision rule I can use. You can determine your own decision rule in order to make your predictions or your classifications. Now, there are actual ways to tune this threshold. Okay? You can tune this threshold by balancing different measures like what's your classification accuracy? What's your type 1 error? What's your type 2 error of your accuracy or your prediction? Okay. All of those things come out of something called a confusion matrix. Okay, hopefully it's not confusing. Right. Okay, so a confusion matrix essentially can take the categorical variables, their true values, and compare them to your predicted values. Here we have predicted values of 0s and 1s now, right? We actually have the true 0s and 1s. We actually know if someone was accepted or rejected, right? What we can do is line up our predictions against the actuals and see. We predicted a 1. Was it actually a 1? We predicted a 1. Was it a 0? Those are the options, right? Or we predicted a 0. Was it a 0 or was it a 1? We can line up the two dimensions using the table command. So table is actually pretty flexible. It can generate counts for you in one dimension. That is, it'll just tell you how many times something occurs. It can also generate counts for you in 2 dimensions. That is, what's the concurrent counts? You'll see what I mean in a second. Okay, if we run this bit of code, you get something like this. You have false and true as 2 rows, and you have 0 and 1 as 2 columns. This entire row here is all of the actual observations. So there's 285 observations in our entire sample where a person was rejected. This entire row here, the sum of it is the number of times in the sample that someone was accepted. The sum, row-wise, tells you the true population of trues. The sum, row-wise here, tells you the total population of people who were rejected. Now, this column here tells me the number of predictions that I had where I predicted someone was rejected. So in our little model we just estimated, our linear probability model, only 6 people were rejected using this decision threshold of 0.5. Using the 1, how many values did we predict were 1? We predicted basically 2,000, pretty much the entire sample was 1s. Everyone was accepted. The intersection here, where it's false and 0, the 1/1 entry of the matrix, row 1, column 1, tells me I predicted false and it was actually false. I predicted rejection when it was actually a rejection. The 1/2 entry, row 1, column 2, tells me I predicted acceptance when the person was actually rejected. The 2/1 entry tells me I predicted rejection and this person was actually accepted. The 2/1 entry tells me this person was accepted and I actually predicted they were accepted. My correct classifications are where inside of this matrix?
Diagonal.
On the diagonal. Here I predicted reject, they were actually reject. Here I predicted accept, they were actually accept. That is my accuracy rate. Here, this is an error. This is a false positive. This is a
false negative.
There you go. Okay. So we can go into this confusion matrix. We can extract the diagonal using the diag command, 5, 2094. If we add it up, that tells us the number of correct predictions we had. We had 2,099 correct predictions. If we divide that by the sum of everything, all of the predictions, that tells us our overall accuracy rate. 88% accurate.
Should have used the average.
It's not really better than guessing, right? Okay. We can look at type 1 error. So predict, reject when it's actually accept. That is the 2-1 entry here. Oh, sorry, here, the 2-1 entry, divided by the sum of the trues. All right, so here I rejected someone when I should have accepted them. Okay, very tiny proportion. We can look at type 2 error. That is, I accepted someone here when I should have rejected them. So basically, I made a lot of this error. I was over accepting people. Okay, and here we can look at basically the accuracy rate in the two separate domains. That is, how many did I correctly reject? I only correctly rejected 1.7% of the total population that was rejected. So I didn't do a good job classifying rejections. How many correct positives did I accept? 99.9%. Because I just accepted everyone, right? So by pure chance, I was very good in this space. Okay. Now, there are metrics that you can actually create that combine different types of, or different measures of accuracy and error, right? One of them is called an F1 score. So if you just Google F1 score, an F1 score is a way of balancing precision and recall. Precision is your accuracy, recall is your errors that you're making. Okay, so there's statistics you can try to tune in order to get a well-balanced model. That is, it balances its ability to correctly predict things with its ability to make mistakes. Okay, and you can adjust this by just simply changing your threshold. Right? By me increasing my threshold to 0.88, I'm going to reject a lot more people. Okay, if I look at my confusion matrix now, that actually looks a little bit better. Right? Here I may be now a little over rejecting. So depending on the decision rule I impose, the decision rule is basically how do I interpret the probabilities from my model? That's how I go from a prediction to a real world action. Right? Because you can also think of this like, maybe this bank had to hire people to go through and evaluate each one of these reports manually. And this was the results, or this was the interpretation of the people that went and reviewed this report. Okay. Now let's say I want to build a statistical model that can replicate the power of what the people did and build it into an automated system. So then people just apply and I can accept or reject them automatically. I can build a linear probability model, hopefully something more advanced, but I can build a model to automate rejections and acceptances, assuming everything's verified. Make sense? Okay. This is really powerful. You can do things like, what's the likelihood of someone having coronavirus? Plug in temperature, plug in height, plug in weight, plug in where they live, plug in lots of other things. And you can try and predict what's the likelihood of this person having this disease. Make sense? Okay. How many of you guys have seen like the Apple app that tells you if you should get tested or not? Or the Google website that was made recently? No? Okay. On those websites, there's basically a survey, you fill out. Do I have this condition? Do I have this condition? Do I have this condition? In the background, what that's doing is it's just calculating the likelihood of you having a disease or not. If you think you have a high likelihood, it'll push you to a testing center and then you'll go get tested. Okay. Google uses all this stuff all the time. How do they figure out where to place an ad on a web page? Was the ad clicked on? Yes or no? Did I get some sort of engagement? Yes or no? I can control for things like the ad it included this word, was on this page, occurred at this time of day, occurred here at this location. Did it get engagement? Yes or no? These are really powerful models. Make sense?
Yes. In terms of using this, so let's say work at a bank, right?
Mhm.
John Doe walks into the bank, you know, it tells me this is how much I make, this is everything, basically, all of those variables, right? Is there a, you know, we can plug it into the model that we saw for all of the variables. We'll calculate what the loan will be, the ratio, and all that stuff. That will give me the probability at the end, right? As to how likely they are to get
Yes,
accepted, given X, right? All the factors. There is at one point, because we're drawing that line where that's no longer going to be the case, right? Where we no longer can't use the model to make those predictions.
How do you mean?
So kind of one of the things that I've seen is like, you know, we're drawing a line, right, through all of the data points, right, for the regression line. But there is an end to that line, right, on that, given the data set that we have, or given the variables and given the observations that we have. Anything that falls outside of that, are we still able to use a model, or am I not making sense?
Not making sense.
Okay, I'll revisit that, and I'll try to send you an email about it.
Okay, sure. But essentially, all you're getting is you take in these features and you predict the probability of someone getting accepted or rejected. There's cool things you can also do, like put in, so you could add another model, right? What's the likelihood of this person lying, right? What's the likelihood of this person giving me a fraudulent application, yes or no? That could be an additional layer on top of this model that feeds into this model. Okay. Okay, let's take a 10-minute break. So I know you guys are probably getting tired. Take a 10-minute break, and then we'll cover nonlinear models. We're going to do it really quickly, and then we're going to jump into GIS. Sound good? Okay, 10-minute break. So come back exactly at 3:10. 9 minutes.
Cool.
Okay, so we just went through the linear probability model. Now we're going to go through the slight variations of the model that are nonlinear. Specifically, we're going to cover the logit model and the probit model. Okay. I really don't want you guys to think these models are anything really all that special, because truth be told, they're really not. They do have some nicer features to them, but they're really not anything crazy. And you'll see why in a moment. Okay. So there's a couple of issues with the linear probability model that we discussed. The blatant, like super obvious one is we don't want to predict out of the 0-1 range. Plain and simple. It doesn't make sense, right? We want our probabilities to be bounded between 0 and 1. So it would be very nice if we were able to map our model to a 0-1 space. That is, regardless of whatever the inputs is, we could squeeze it into 0 or 1. So it's a really big number, make it really close to 1. If it's a really, really tiny number, make it really close to 0. Okay, so that's one thing we want to address. The second thing we want to address is really introducing nonlinearities. That is, when we were talking about the payment to income ratio in the loan applications, right? We said if you go from 0.33 to 0.34 payment to income ratio, it's going to reduce your likelihood of getting accepted by 0.5%. If you go from 0.9 to 0.91, it's still just reducing your likelihood of getting accepted by 0.5%. Okay. One nice thing that we could do is induce a nonlinearity. So there's a difference in the marginal effect. That is, if you go from 0.9 to 0.91, it's slightly different than if you go from 0.3 to 0.31. Okay. Now, we can do both of those things actually in one very nice, elegant step. Okay. Essentially, all we have to do is take our linear regression and map it through a function g. Okay, so we're going to create a new function. We're going to call it g. this magical G function is going to take whatever values of x beta, whatever it is, from minus infinity to plus infinity, and it's going to squeeze it into the 0, 1 range. Okay. By doing that one step, we automatically just solve both of the problems we talked about. Here's how. Okay. Typically, what we'll use for G as a definition is called a logistic function, which is this thing. It's basically just taking the exponential of some number z divided by 1 plus exponential of z. This is going to map any number z from minus infinity to positive infinity into the 0, 1 space. If z gets really close to positive infinity in the limit, then g of z is going to tend to 1. If z tends to minus infinity in the limit, then g of z is going to tend to 0. Okay, and you can usually denote this logistic function by capital lambda. That's all this is. So lambda of z. Okay, this is called a logistic function. When you use this generic version of G, when you use a logistic function for G, we call it a logistic regression. That is, see how here there's a Z? If you replace that with x beta, that's your logistic regression. So you put x beta up there, you put x beta down there, that becomes your logistic regression. Okay. Another formulation you can use is something called a probit regression. In a probit regression, you don't use a logistic function, you actually use a standard normal density function instead. So instead of using a logistic function to map everything from 0 to 1, you can use a standard normal function to map everything from 0 to 1. Right? A normal distribution, its limits are minus infinity to infinity. The cumulative distribution function, the CDF of a normal distribution, just goes from 0 to 1. You can't have any likelihood greater than 0 or 1, right? Now we know in a standard normal though, right, the most likely outcomes are around the mean, right? Within 1 standard deviation, 2 standard deviations, or 3 standard deviations. Everything outside of that range is pretty much as likelihood of 0 of occurring, right? Okay. To get a sense of actually what's going on, if you take this function, e raised to the power of z divided by 1 plus e to the power of z, here e is the exponential function, right, the inverse of natural log. And if you plug in the probability density function for a normal distribution, you can plot out the CDF of a logistic function against the CDF cumulative distribution function of a logistic regression. So in blue here, we're taking in a value or a number z, and we're mapping it through this function g of z. Where in the blue line, g of z is the logistic function here. The red line is the normal distribution function, or standard normal distribution function, which is here. Okay. The logistic function is a little bit flatter. By that I mean it actually assigns higher probabilities, or its steepness is less, so it assigns probabilities in steps that are larger. Right here, there's sort of there's a sharp increase in the probability around 1 standard deviation. Okay. In both of these functions, if you pass in 0, that's exactly where you're at half of the likelihood of something occurring. So g of z, or g of 0, if you're using a logistic function or if you're using a standard normal function, it's still 0.5. It doesn't make a difference. Okay. Both of these models give you the same results, usually the same results as a linear probability model. Usually, and I'll explain why in a second. And they usually give very similar results to one another. Okay. Now, we're not going to cover how you actually estimate these things, because here you can't, there's not a closed form solution like you do in ordinary least squares. The way you actually estimate these sort of models is through maximum likelihood estimation. And by that, I mean you basically do like a numerical optimization where you keep plugging in and changing the values of beta until you maximize the log likelihood of this sample coming from the predicted values of your model. Okay, it just becomes a numerical optimization. Okay, what I want you guys to focus on though is solving those two things we talked about. One, mapping the space so it's always between 0 and 1. That's kind of obvious here, right? You plug in 4, it turns it into 1. You plug in -4, it turns it into 0. And that extends in both directions, right? So if you plug in 100, it's basically 1. If you plug in -100, it's basically 0, right? No matter what, the results of logistic regression are always going to be bounded between 0 and 1. That solves problem number 1. Problem number 2 was this idea of inducing nonlinear average partial effects, or nonlinear partial effects in the interpretation of the model. Okay. If you actually pay attention to how this model is specified, which is basically this, right? I'm using this new function G, capital G, and I'm putting it around my regression. There's my same regression from before. Trying to understand the probability of a mortgage getting accepted conditional on X, where X is all of these things. So I'm taking my linear regression and I'm mapping it through this function G. Okay. Now, how did we come up with partial effects before? How did we interpret our models before?
Just take the partial derivative.
Exactly, you just take the partial derivative, right? Okay. Now, just on the structure that we have here, right? We're saying, what's the probability of our mortgage?
Are you sharing the tablet screen or the iPad?
Yeah, do you see that?
No, I don't.
You see it? Okay.
No, I don't. Thank you.
Probability of my mortgage getting accepted. Conditional on beta 0 plus beta 1, payment to income. I'm just gonna beta 2, loan to value, plus beta 3, unemployment, plus beta 4, African, plus epsilon. Right, this is our regression now. Yes? If we take the partial derivative this time around, it's actually a little bit different. The reason is we have to use, what do we have to use if we take the partial derivative here? Let's say we take the partial derivative with respect to payment to income again. Regardless of the function G, we need to use something called the chain rule. Whenever you have a dependent variable inside of a function, you need to differentiate the function with respect to that variable. So first, big G, we're going to call now little g, where little g is the first order condition of big G. So we're going to say little g dot is equal to G prime dot big G. Okay. Put that aside for a minute, or I'll write it over here. G dot is equal to big G prime dot. So dot is whatever the function takes in. It's going to be G of beta 0 plus all of this stuff. I'm just going to call it X beta. Multiplied by, so it's the derivative of the outside times the derivative of the inside. This is now the derivative of the outside. The derivative of the inside is okay, so again, here we're using the chain rule.
So you end up multiplying the effect.
So now we have beta 1 as our partial effect. But our partial effect is dependent on the X we plug in. And it's not just the X we plug, it's all of the X's we plug in. Right? What loan to value ratio do I plug in? What payment to income ratio do I plug in? What unemployment do I plug in? Do I plug in a 1 for African? Do I plug in a 0 for African? Depending on what I plug in for each of those values, I'm going to get a different partial effect.
So it's also depending on the value, that is going to be multiplied times that coefficient, and then it will be multiplied times the partial effect.
You got it. Now, the two most commonly used methods for actually figuring out what values to plug in are, one, so this is where it starts to get really interesting, because now you as an econometrician have to decide what's the partial effect you want to study. Okay. The two most commonly used, one is called the partial effect at the average. All that's going to do is it's going to go into G, and it's going to plug in beta 0 hat plus beta 1 hat times x1 bar, the average for x1, plus beta 2 hat times x2 bar, the average for x2. That is just the average across the general sample, plus everything else at its average, multiplied by beta k, whatever it is. Okay, so here it's just a generic y, and here it's the derivative with respect to a generic xk. Okay, this is the partial effect at the average. There's some problems with this though. For instance, here we said we had one dependent variable that was African, that is the person of African American descent. Well, what's the average of a 0-1 variable? 0.4% African or 40% African? I mean, yeah, people can, be like a mix of something, but that doesn't really represent anyone in our sample with the way it's coded up. In our sample, you're either African American or you're not, right? Which in and of itself is a little, absurd, but still, that's how it's coded up. Or you can imagine it as a better example is male or female. Not really anymore a good example because you can be somewhere in between, right? But in that case, you could be, if I have 10 males in my sample and 70 females in my sample, the average is, right, 1 out of 8. If the males are coded as 1s, and depending on how you code it up as 1s or 0s, right? That may be a difficult thing to interpret then, because that person that you're plugging in to this model may not actually exist, or that unit you're plugging in may not actually exist inside of the sample. Because that's a weakness of this. Which brings us then to our second version. The second version is called, so this is a little confusing. So there's partial effect at the average, and then there's also average partial effect. Or another way of phrasing it is the marginal average effect. Average effect. Okay. So this is called the APE or AME. Right? Or sometimes MAE, depending on the software you're using. Average marginal effect or marginal average effect. The difference is, in this specification up top for number 1, you're plugging in the average x1, the average x2, you're plugging in the averages of each of the respective variables, okay? The alternative is actually go through and calculate everyone in your samples beta 1. Oops. For everyone in your sample, actually go ahead and figure out, so plug in every single person's X1, plug in every person's X2, basically get the predicted values of every single person in your sample, feed that through the first order condition of whatever G is, and average it. Whoops. And then take all of that and multiply it by beta hat k. So there's two different versions. One, I'm plugging in just the average x's, which is here. Two, I'm actually coming up with the full predicted value for this individual and averaging across everyone's predicted values and using that as my scaling factor. In either case, I'm inducing a nonlinearity. By that I mean, depending on the values of x I impose, I'm going to have a different partial effect. The partial effect is going to vary depending on where this person falls in the sample. Make sense?
Makes sense.
Okay. We'll jump out of there and we'll jump back into R really quickly, or rather, let me share my desktop screen now. Okay. So this is what we just derived, right? In general, we have for any xk, you're always going to be taking the first order condition of G. You're going to be evaluating x beta hat at that first order condition, and you're going to be multiplying it by beta k. Okay. For that, you need to know then, well, what's little g? Okay. Well, if big G is this function, you can differentiate it with respect to z, and you'll get basically the exponential of, or here I have it in terms of x, the exponential of x divided by 1 plus exponential of x squared. That'd be the first order condition of big G. And here's the first order condition when you're using a normal distribution. Okay. This is the discussion of the partial effect at the averages and the average marginal effect, or marginal effect at the averages, these two. Let's walk through an example of just re-estimating our model now using a logistic and a probit, and we'll talk about then how we interpret these different partial effects. Okay? Okay, so I've gone ahead and I've coded up here two functions for us. The logit partial derivative, that is little g. So this is little g, the first order condition of the logistic regression. And this is little g, which is the first order condition of the probit regression. Right? And it's not really the regression, it's actually like the distribution or the function, logit function. Okay. So if we're going to be doing things like calculating the partial effect at the averages, we're going to need the averages. So what I've done here is I've just gone back into our data set that we've been looking at. I've selected out the 4 columns we've been using: payment to income ratio, loan to value ratio, unemployment ratio, or unemployment of that person's industry that they work in, and the indicator of if they're of African American descent or not. Okay, I'm calling all of that X data. Now in X data, if we preview it, we'll see that here African American is coded as no or yes. I can't take the average of no and yes. I can take the average of no as 0 and yes as 1. Then it would basically be what's the fraction of the population in which they are of African American descent. So here I've gone ahead and I've gone back into the AFAM column, X data AFAM. I've converted AFAM from a factor into a character, and then I've converted that into a numeric after making sure it's a yes. So then now if we do head X data, we'll see that the previous no's are now zeros, and wherever there's a true, or wherever it was a yes, it's now a 1. Okay. We can go across each column, this column, this column, this column, this column, and calculate the average. And that'll be the like X bar 1, X bar 2, X bar 3, etc. So here I'm going to go using the apply command. I'm going to do exactly that. I'm going to go into X data. I'm specifying index 2. So go column by column. I'm going to apply the command function, or I'm going to apply the mean command. So I'm going to take every column. I'm going to calculate its average. So means data now contains the averages of each of those columns. Okay. Now, to actually estimate a logit model, I don't use LM, I use GLM, generalized linear model. Okay. The way you work with a GLM object is exactly the same way you work with a standard LM object. My dependent variable is accepted. I'm regressing it on payment to income ratio, loan to value ratio, unemployment of the industry. If they're African American, I specify the data. Now, the GLM function has the ability to actually fit a huge family of models. That is, it can work with things like count data, it can estimate a logit model, it can estimate a probit model, it can estimate lots of stuff. We're only going to use the GLM for using logistic and probit, but I want you to look at the documentation because this one function has a full class of families of different types of data that you can work with. Okay. So here we're going to specify we want to use a family or a model from the binomial distribution. We're going to specify something called the link function, G, as the logit function. Okay. So here, by specifying the family as a binomial, we're saying we're going to do a logistic regression by specifying the link function as logit. Alternatively, we can specify the link function a little bit lower down as probit, and then we'll be using the standard normal rather than the logistic function. Make sense? It's just syntax. Okay, so if we run this, we'll have a new object called logit model. Okay, again, we're going to want to use our robust standard errors. Okay, this is the estimated coefficients in our logistic model. These coefficients are utterly meaningless. Can you repeat that for me? Everyone. These coefficients are utterly
meaningless.
Thank you very much.
Yeah,
Okay, I don't think I heard everyone. Can we try that one more time?
yeah.
These coefficients are utterly meaningless.
Thank you. Okay, these coefficients are meaningless. The reason is we don't really care about the coefficients. What we care about is we care about the partial effect, right? What's nice about a linear probability model, or what's nice about using ordinary least squares, is the coefficient is the partial effect. That's the interpretation. I cannot interpret -5 because we know I have to take the first order condition of whatever link function I used. Here, the link function I used is the logit function. I have to plug in certain values for the x's, then I can multiply it by this coefficient to actually be able to interpret its partial effect. So again, these coefficients are utterly meaningless, except for one thing. Here's the exception. Ready? When we're taking this first order condition, like this, the logit function is positive, or the link function we're using, your big G, it's positive. Because of that, we're always going to maintain the sign of the coefficient. That is, if beta is negative, then the partial effect is negative. If beta is positive, the partial effect is going to remain positive, regardless of everything else. That's going to be the same if you're using logistic regression or probit regression. So the sign does matter. Everything else, meaningless. The numbers don't mean anything. The only way you can interpret the numbers is by actually
Plugging in.
calculating the average effects. Okay? But you can do the exact same things we did before. You can generate predictions. So if you go into the, you can use the predict function on the logit model and generate predictions for you. However, if you want the logit model to predict for you probabilities, you need to specify the type as a response. Otherwise, if you use the predict function in R, all it's going to give you is x times beta. Okay? You don't want x times beta. You want x times beta mapped through G, the logit function. You can specify this option type equals response, and that'll map everything into a probability for you. So now our logit predictions, if we do the range of logit predictions, they're bounded between 0 and 1. I can check that off my list. I can still calculate discrete choices, so I can do a classification. If my predictions are greater than 0.5, make it a 1, otherwise make it a 0. I'll call that logit binary. I can check how well that performed. So using the same threshold of 0.5, I actually got a slightly different result. Before, I only had 5 in this entry. Now I have 15, so actually I did a little bit better. I was able to draw a boundary between the zeros and ones a little bit better using a logistic function. Okay. So you can go back and calculate, what's my accuracy rate? What's my type 1 error? What's my type 2 error? Now, to actually interpret the model, we said you have two options. You can either calculate the partial effect at the averages, that is, plug in the average x for each x, or you can calculate the average marginal effect, in which you actually calculate this little function for every single observation you have, average it across, and then use that as your scaling factor. Okay, and that'll give us then the actual interpretation for the coefficient. This is the thing we actually care about. Okay, so here I've written the code for you that does that. Basically, we're going to go into the coefficients. There they are. We're going to dot product the coefficients with the averages, the means data we created. We're going to feed that then through our logit partial derivative, little g, which I didn't define. Then we're going to take each of our individual coefficients and multiply them by that one constant term. And those are now our partial effects at the averages. That is, for every, this is the average x bar times beta. Okay, there it is. Oops. So now this is our partial effect at the averages. We said the alternative is actually go through and predict x beta for all of our observations, feed that through the partial derivative, little g, calculate the average of those things, 0.094, then multiply that by each of our coefficients. That gives us then our average marginal effect, or our marginal effect at the averages. Okay, the numbers are slightly different. This is the log marginal average effects. This is the log of the partial effects at the averages. So here's our coefficient on African American, a little bit lower when using partial effect at the averages, a little bit higher when using marginal effects at the averages. Okay. Now, rather than writing out the code like this, there's actually a package called margins that'll automatically do this for you. Oops. Sorry, I'm going a little bit quickly, just because we're basically out of time. Okay. What you can do, though, is stick together and compare the coefficients from, so this column here is the coefficients from our linear probability model. The coefficients from your linear probability model are the partial effects, right? It is the first order condition. The first order condition with respect to any xk is just beta k. You can compare these estimates to the partial effect at the averages or the marginal effect at the averages from a logit or probit model. So if you scroll down, it's exactly the same code here, just using a probit. So if I run all of this, I think at the bottom I have all of them side by side with each other. They're all very close.
How can you see the significance of those new coefficients? If
the statistical significance is just going to be given by, it's in the COEF test, it's there.
okay,
But here I just have the point estimates so that you can just compare. Generally speaking, if it's significant in one, it's going to be significant in all of them. But here, the key thing to measure is basically, are we getting the same results? You should always get the same sign, regardless of if you use a logistic regression, a probit regression, or a linear probability model. The magnitude should be roughly the same if you're using a logistic, a probit, or a linear probability model. This is really telling you that a linear probability model is super badass. And the reason is, it's extraordinarily simple. It's just standard OLS. But it gives you a very easy interpretation. You don't have to do any of this partial effect at the averages business. You don't have to do any of the marginal effects at the averages business. It doesn't matter what x's you plug in. You just get one constant effect, which is a simplifier. It just makes it extraordinarily easy to interpret. And it's really not all that different. You do usually get some better predictive power, like better classification accuracy when you use a logistic or a probit. But it's really not that much more special than just a simple linear probability model.
as long as you're using the robust estimators.
Okay. We don't have time to do the GIS stuff, which is annoying. So I'll just introduce it next week before you guys do your presentations. So I'll take like 30 minutes out of the class at the beginning. And I'll walk you guys through how to view map data, what it looks like, and just give you an introduction. I think at this point, you guys have enough skills to probably be able to go through it on your own pretty quickly, but we'll introduce it next week. Another thing I've included in here is this command called stargazer. Okay, here I've feeded in the linear probability model, the logit model, the probit model. If you do that in R, it'll generate these nice regression tables for you. Again, though, the coefficients here, meaningless. So this is actually a mistake. You don't ever want to report these coefficients. No one gives a shit about these coefficients. What we care about is the partial effect. Okay, and I've seen so many people make this mistake, it's embarrassing. You don't care about the logistic regressions coefficients. What you care about
Is a partial effect.
Is the partial effect. And in order to get the partial effect, you need to do it you need to make some assumption. You need to either do it at the averages or you need to do the marginal average effect. Know it. Memorize it. And if I ever see any of you at a conference presenting this, or if next week on your project you present this, I'm not going to be nice.
Yeah, this is before averaging, isn't it?
This is just the coefficients. They're meaningless.
Yeah, exactly.
Okay, so typically you'll report the averages or like the marginal effects, and then here you'll write a note as to how you did it. You'll say average partial effect at the averages, or you'll say marginal effects. So that's it for this week. That's really it for the class.
Hi, Sam. When are you gonna post this video up?
I'll try and post it up tonight.
No, great. Thank you.
Yeah. Any other last minute questions?
Yes, sir. So we are saying that in any model, in any regression run in logit or probit, we have to undertake the two-stage operations where we have to average. No way out, isn't it?
No way out. You need to calculate the partial effects in some way.
Okay, thank you.
Sam, are we going to have a final or not?
I'm debating it, but if we do, it's going to be like a homework assignment.
Okay, thank you.
Next week, presentations. So be prepared to share your screen with your group and walk us through your presentation. Be prepared to answer questions. How many groups do we have in total at this point? Is everyone working on their own, or do you guys have partners? I think last I checked, there's like 5 or 6 groups. Okay, so budget roughly 15 minutes and 5 minutes for questions. So 20 minutes total.
That was good.